Next problem. FK, the measure of FK is 5. And keep in mind everything you know about a rhombus. We know that the diagonals bisect, we do know the diagonals bisect each other. But not only do the diagonals bisect each other, they also bisect these angles, and they're also perpendicular. Remember all that stuff. FK is 5. So the distance from here to here is 5. What's the distance from here to here? 5. Do we know the distance from here to here? No. That's actually what we're looking for, right? KJ. So we have this is 5. We have this FG is 13. You sure can. In a rhombus, the diagonals are perpendicular. So you're gonna encounter that same Pythagorean theorem that we've been using for distance formula for all these other things. And that is a Pythagorean triplet. 5, 12, 13. A squared plus B squared equals C squared if you'd like to do it. But that's not what it's asking us for. It's asking us for KJ. Is KJ also 12? Why? Why do they bisect each other? Because it's a rhombus? More than that, because it's a parallelogram. The diagonals of a parallelogram bisect each other. So if that's 12, this is 12. If that's 5, this is 5. If that's 13, they're all 13. Why are they all 13? Because it's a rhombus. All the sides of a rhombus are the same. Another, the measure of angle F or JFK, there we go, President JFK. JFK, which is this, is 6y plus 7. 6y plus 7. The measure of KF, not KFC, but KFG, KFG is 9y minus 5. You'll help me out with that one. What's going to be true about those two angles? They're equal. Now, what about this? Let me ask you this. Would this angle also be equal to, I don't know, let's say this angle?
Yes.
Yeah. For a couple of different reasons. Does everybody see the Z there?
Yes.
This is a parallelogram. You have parallel sides. You have a transversal. You have that Z shape. Those are alternate interior angles. What about this? Would that angle here be congruent to this angle? And now I've got you thinking in the wrong direction because you're thinking, well, parallel lines, I don't know. There's other reasons. There's several other reasons that you could list. Is this an isosceles triangle?
Yeah.
Sure. Why? Because this is a rhombus, so the sides are the same. So does that not make those two angles the same? Here's another reason. Is this not a parallelogram? Are the opposite angles of a parallelogram the same? Sure. So this whole angle equals this whole angle. But not only that, since these opposite angles are the same, well, since it's a rhombus, doesn't this diagonal bisect this angle? Cut it perfectly in half, and it also bisects this angle. So if this was 50 and 50, then each of these four little pieces would be 25 and 25. Okay. But now back to this problem. The diagonal, or a diagonal in a rhombus, will bisect the angle. So therefore, these two angles must be equal. 9y minus 5 would have to equal 6y plus 7. Move all my y's to the left side, Hunter. How many do I now have?
3.
And move anything else to the right side. What do I have it equal to?
12.
So y is 4. We always like to plug it back in just to make sure we're right. If y is 4, that gives me 31 degrees here. And hopefully the same thing here, 36 minus 5, which is also 31 degrees. And now if you want to define everything else, folks, 31, 31. This would be 59, because I know that's a right angle. 59, 59, and 59. Any questions? This would be equal to this would be equal to this, and all four sides is equal as well. Squares. Next to the last shape that we're going to do, well, next to the last quadrilateral we're doing. A square is a parallelogram with 4 congruent sides and 4 right angles. We already knew that. A square is, again, a square is a child of a rhombus and a rectangle. It has all the different characteristics of a rhombus. It has all the different characteristics of a rectangle. Recall that a parallelogram with 4 right angles is a rectangle. A parallelogram with 4 congruent sides is a rhombus. Therefore, a parallelogram that is both a rectangle and rhombus is a square. So here's all your shapes that we've done thus far. Here's all the shapes that you're going to have to know the properties of. Rectangles, rhombi, parallelograms, which is the general category up here, and then your squares here. Conditions for rhombi and squares. And again, conditions is how do I prove it's a rhombus? How do I prove it's a square? That's what a condition is. First off, a condition for a rhombus. If the diagonals of a parallelogram are perpendicular, diagonals are perpendicular, it is a rhombus. So that's the first one you write down. Second one, if one diagonal bisects a pair of opposite angles, then the parallelogram is a rhombus. And notice it says one diagonal. You don't even have to test both. If angle 1 and that is congruent to angle 2 and angle 3 is congruent to 4, if that one diagonal bisects this angle, then you've got a rhombus. So one diagonal bisects a pair of opposite angles, then it is rhombus. If one pair of consecutive sides of a parallelogram are congruent, one pair of consecutive sides are congruent. Now, why do they have to be consecutive? Why can't they be opposite sides? Well, all parallelograms have opposite sides that are congruent. And the square is pretty easy. Easiest thing that we've done in this chapter. To prove this, that's the 3 ways you can prove something's a rhombus. Now, to prove something is a square, all you've got to do is prove that it is both a rectangle and a rhombus. If it is both a rectangle and a rhombus, then it's a square. So do we need to know all those properties, or conditions of a rectangle, which there's only 2, right? Conditions of a rectangle, if you have a single right angle, or if you have diagonals that are congruent, then you have a rectangle. And then you would test to see, is it a rhombus by using one of these 3 conditions, and if it's a rectangle and a rhombus, then it is also a square. We're not going to actually do this proof, but here's a proof for you to look at. It says write a paragraph proof, and here's your actual proof here. We'll read it in just a second. We're given that we have a parallelogram, and we're given that JKL is isosceles. JKL is isosceles. Well, think about that. If this is a parallelogram, let's just use our common sense here. If this is a parallelogram and that JKL is isosceles, that means those 2 sides, by definition of isosceles, does that not mean that these 2 sides will be congruent? And we want to prove that this is a rhombus. Are we not pretty much done? Look at your 3 conditions for rhombi. What was the third one? One pair of what? Consecutive sides are congruent. Is that not what we have here? KL is congruent to KJ, so therefore, since one pair of consecutive sides is congruent, then it's a rhombus. And that's what they're going to do here. Since it is given that JKL is isosceles, then KL is congruent to JK, like I marked. By definition, that's what isosceles means. These are consecutive sides of the given parallelogram, so by theorem, they call it theorem 6.19. I don't like that. Since one pair of consecutive sides are congruent, then JKLM is a rhombus. The reason I don't like for you to put by theorem so-and-so, it really depends on the book, and I pull a lot of my material from different books, so it might be theorem 6.19 here, but more than likely, well, no, it was theorem 6.19 there as well. So write a paragraph proof, and let's not write a paragraph proof. Let's just go through this and talk about why this would be true. We're given that SQ is the perpendicular bisector of PR. SQ, PR, perpendicular bisector. So that means that these are the same. Perpendicular, that's what you've got there. SQ, oh, I wrote that backwards, didn't I? SQ is the perpendicular bisector of PR. So that means this is the same, and that's perpendicular. Well, but then it turns right around. PR is the perpendicular bisector of SQ, which means that that is also equal to that as well. RMS is isosceles. RMS is an isosceles triangle. So now what does that mean? What can I do with that? We're perpendicular bisectors of each other, so these are the same and these are the same. But then it says RMS is an isosceles triangle. How can I change my drawing now? What's going to be true about PM, MR, MQ, and MS? They're all the same. Okay? Since this is isosceles, that means that these two would be the same. Now what tells us that? If these two are the same, then why would these two be the same as well? That is the transitive property. And I lied to y'all the other day. We use reflexive. I don't remember if you remember the day. Y'all were telling me transitive. I said, no, that's reflexive. Y'all were right. It was transitive. Same thing here. MR and MS are the same because it's an isosceles triangle. Since those are the same, then these will also be the same. So I can just put a single tick mark on all that. Let's go back and do that. These are congruent, and you have a right angle. Prove that PQRS is a square. In order to prove that this is a square, we've got to prove that it is a rectangle, and we have to prove that it is a rhombus. Is that a rectangle? There's only two ways that you can say that this is a rectangle. This has to be a right angle, or the diagonals, like you said, the diagonals have to be congruent. Are the diagonals congruent? Yes. So since the diagonals are congruent, we can say it's a rectangle. Now is it a rhombus?
Yes, the diagonals.
The diagonals, not bisect. Now diagonals bisect each other. That tells you it's a parallelogram. If the diagonals are perpendicular, then it's a rhombus. So this is a rhombus. And since it's both a rhombus and a rectangle, that leads us to know that it is also a square. That would be a very tough proof because that's a lot of steps that we just listed. The key to a successful excavation of an archaeological site is accurate mapping. How can an archaeologist be sure that the region they have marked off is a 1 meter by 1 meter square? Well, first off, in order to be a square, let's go through the entire proof. Is it a parallelogram? Does it even say anything? It doesn't. Is this a parallelogram? Sure. How do you know it's a parallelogram? Opposite sides are equal. 1 and 1, 1 and 1. Anytime you have that, it's a parallelogram. Okay, now that we know it's a parallelogram, is it a, let's see, what are we going to go to next? How could we determine that it is a, because we know it's a rhombus. Everybody good there? If all the sides are the same, it's a parallelogram, all the sides are the same, it's a rhombus. But how can we be certain that it's a rectangle? That's what they're asking pretty much. Not necessarily, not a rectangle. With what they're given, no. But what they're saying is, how can he be sure that it would be? What could he do? Well, he doesn't have a protractor, unfortunately. If he had a protractor, he could measure to see if this is a right angle, or what's the second method he could use? He could make diagonals. He could measure from here to here, and he could measure from here to here, and make sure those distances are the same. What should be the distance? How are we going to do that? Watch this. This will make your head hurt, guys. You don't have to. What kind of triangle is that? And not only is it isosceles, but if this is a right angle, what kind of right triangle is that? It's isosceles. That means that each of these would equal 45 degrees, would it not? That is a 45, 45, 90 right triangle. Again, everything just swarms back. It comes back and haunts you, right? So the relationship in a 45, 45, 90, the legs will be the same. And how do you go from leg to hypotenuse? Multiply by So that'd be 1 times root 2. So each of your diagonals should be root 2 in length. Moving on. Determine whether this is a rhombus, rectangle, or a square. List all that apply. I like this because it doesn't say use distance, use midpoint, use slope. It allows you. Notice something? It is a parallelogram. They give you that. You don't have to check to see if it's a parallelogram. They give it to you. So let's go through, is it a rhombus? How can we determine if it's a rhombus? Go through your list. I think there's 3 of them, right? All 4 sides are equal. Or does it have to be, well, since it's a parallelogram, yeah, we don't have to go through all 4 sides, do we? We just have to do 1 set of sides. Remember that? Because it is a parallelogram. Y'all see that? So these are equal and these are equal. So if we can just prove that these are equal, it's a rhombus. Or, say it again, diagonals are perpendicular. Now, how can we determine if the diagonals are perpendicular? What formula are you going to use? Slope. If the slopes are opposite reciprocals, then the diagonals. So pretty much it's, do you want to use the distance formula? Do you want to use the slope formula? Or what's the third way? The diagonals bisect the angles. Now, how would you figure that out? You might have to use some trig there, so let's stay away from that one. Let's use distance. Let's prove that one consecutive set of sides is congruent. Doesn't look like it, does it? Draw your little right triangles. I have side lengths of 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 7. And this one is 2 and 1, 2, 3, 4, 5, 6, 7, 8, 9. You wouldn't think, right? I mean, what's the chances? The first one. Help me out, Matt. We've got to find the distance from here up to here. We're going to use Pythagorean theorem, a squared plus b squared, Matt. What is a squared plus b squared? There you go, 36 plus 49, which is 85. So therefore, c squared is 85, so what's c going to be? Root 85. Everybody good there? Everybody understand it? Look at the other one. 2 and 9. Help me with it, Colton. A squared plus b squared, what do you get? 85 again, don't we? So this is root 85. So is this a rhombus? Yes. Now, again, we don't have to test all 4 sides because of this, folks. If this is root 85, this is root 85. If this is root 85, it's a rhombus. So now that it's a rhombus, is it a rectangle? Okay, let's erase that. We know it's a rhombus. Let me see if I can blow this up and make it even bigger. And yeah, that's what everybody's going to look at this and say, that's not a rectangle. And I'll say, why is it not a rectangle? They're going to say, doesn't look like a rectangle. Yeah. Well, what if your calculator, you've got these weird, skewed, what do you call it? Your, I just went blank. Your scale, there you go. Your scale is off. Your X scale and your Y scale, you stretch it further one way than you did the other way. Sometimes it doesn't look like it. Sometimes circle look like ellipses and stuff on your calculator. So let's just make sure. The best way to check see if this is a rectangle, let's check see if this is a right angle by using slope. We've got a slope of this side is 1, 2, 3, 4, 5, 6. Rise 6, run 1, 2, 3, 4, 5, 6, 7. We have a slope of 6/7. In order for this to be a rectangle, Trace, we'd have to have a right angle right here, right? So in order for this to be a right angle, Trace, what would the slope of this line have to be? Perpendicular lines have what kind of slope? Negative, close, negative 7/6. They have to be opposite reciprocals, but look, guys, that's definitely not negative 7. Nowhere near. Negative 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 2 nines. And again, you can tell by looking at it, that's nowhere near a rectangle. Okay. And these look very square, and if that's square, then that's more than likely your scale is good on it. So, okay, now let's do the same thing for this one. Now, does that? Oh, Well, I skipped square. It's not a square. Okay, if it's not a rectangle, it's not a square. Because the only way to prove it's a square is to prove it's both a rhombus and a rectangle. So all that is a rhombus. Now this one. Let's do it different. It looks like a square, definitely. Let me get my lines here so it looks a little bit better. Let's first prove it's a rhombus. And the way we prove it's a rhombus is we can do what we just did, to where we prove that this side equals this. Any consecutive sides is equal. Let's do it the other way this time. Another way to prove that you have a rhombus is to prove that your diagonals do what? Bisect, right? So let's try that. Let's try that method. And you just pick the one you like. Do they look like they bisect? Or excuse me, not bisect. Did I say bisect? The diagonals should be perpendicular. And the way, because if the diagonals bisect each other, that means it's a parallelogram. That's it. If the diagonals are perpendicular, then it means it's a rhombus. So let's find slopes. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And instead of 9, let's go back to 8. Negative 8 over 14. Is that slope? And from here to here, we have 1, 2, 3, 4, 5, 8, 9, 10, 14. 1, 2, 3, 4, 5, 6, 7, 8. So the slope of this line, 14 over 8. Negative 8 over 14, positive 14 over 8. Jagger, are those perpendicular? Yes. Why? What's true about your slopes there? Perfect. Anytime you have opposite reciprocals, those are perpendicular. And anytime those are perpendicular, we can go ahead and say we have a rhombus. That makes sense. You know how that works? Think about that. If you have a right triangle here, you see the right triangle? Well, don't we know that the diagonal, since it's a parallelogram, the diagonals bisect each other? So we know that that would be true. Well, if you've got right angles here, and do you see this triangle looks very similar to the other three? All 4 of those triangles are the same. If all 4 of those triangles are the same, then we know that all 4 hypotenuses will be the same, and it has to be a parallelogram. Yeah. Now that we know it's a rhombus, now let's prove it's a rectangle. Now, how can we prove it's a rectangle? You sure could. Sure could. Or that's where you're headed with it. The diagonals have to be the same length, right?
Or you can see if
Is there somehow we can use that 8 and 14 and 14 and 8? Think about this. See if you can picture this. When I counted up 14 and over 8, do you see that right triangle there? Well, so you're going to have leg lengths of 8 and 14, right? Well, what about this other diagonal? Didn't you have also if you drew a little right triangle there, didn't you have leg lengths of 8 and 14? Are those diagonals the same? If you do a squared plus b squared equals c squared using 8 and 14, you're going to do the exact same problem for both diagonals to find the length. So therefore, once you perform that, you're going to get c is going to be the square root of whatever you get when you combine these. You're going to get the same c. So those diagonals are congruent. So not only is it a rhombus, since the diagonals are the same, and that's not the only way to work it. You could find the slope of this side, the slope of this side, and you can see, do I have a right angle there? So not only is it a rhombus, but it's also a rectangle, and since it is both, it is also a square. Any questions? Trapezoids. This is your last quadrilateral. You know everything, hopefully you know everything about parallelograms. You know everything about a rhombus. You know everything about rectangles. You know everything about squares. That's all your parallelograms. So now what if you only have one set of parallel sides? You have a trapezoid here. A trapezoid is a quadrilateral with exactly one pair of parallel sides. The parallel sides are called the bases. And you see that there. If you don't already know that, write it down. You have bases that are parallel, and then you have two legs. Most of you. The non-parallel sides are called the legs. The base angles. Here's base angles, and here's base angles. If those base angles are congruent like I just marked, then you have an isosceles trapezoid. If the legs of a trapezoid are congruent, then you have an isosceles trapezoid. Here we go. Here's your theorems. Here's your properties. If a trapezoid is isosceles, you already know this. It's the same thing as with a triangle, an isosceles triangle. If the legs are the same, the base angles are the same. That's what makes it isosceles. If a trapezoid has one pair of congruent base angles, then it's going to be isosceles. If a trapezoid, that's your second theorem. I'll give you a second here in a second to write it down. If a trapezoid has one pair of congruent base angles, then it's going to be isosceles. You don't have to even check both of them. If it's got one pair, we already know these are, let's go over that. How do we know that? You have a trapezoid here. Don't we know that these are parallel? If you know that only one pair of parallel, or one pair of consecutive angles here, base angles are congruent, you know automatically that this is an isosceles trapezoid. Why? What's the relationship between this angle and this angle? They are supplementary. Those are same side interior angles. Those are supplementary. Well, aren't these two also supplementary? Aren't supplements of the same or congruent angles also congruent? So would those angles not also be congruent? That makes sense. So if you have one pair, then really you're going to have two pairs, and it's going to be isosceles. And the third, final. A trapezoid is isosceles if and only if. Now let's discuss that if and only if. Well, that goes back a long ways. An if and only if statement is called a biconditional statement. A biconditional statement works forwards and it works backwards. So honestly, this is two theorems. This theorem states a trapezoid is isosceles if its diagonals are congruent. So if you see that you have an isosceles trapezoid, guess what? Its diagonals are congruent. But what else can you do with that? If the diagonals are congruent, then you have an isosceles trapezoid. So how can we prove that we have an isosceles trapezoid? Well, if we see the sides are the same, that's the definition. That's an isosceles trapezoid. Or if we have a single set of congruent angles, base angles, it's an isosceles trapezoid. Or if the diagonals are congruent, then you have an isosceles trapezoid. What other shape has diagonals that are congruent? There's a lot of overlap here. A rectangle has diagonals that are congruent, and a square. Does a rhombus? And here, if I ever get confused, here's what I do. I think about extreme cases. Is that a rhombus? Could that be a rhombus? Sure. Would the diagonals of that be congruent? Does that make sense? Think about an extreme case and ask yourself, well, is it always the case? Now, if the diagonals were congruent, it would turn a rhombus into a square. Here's your proof, because we all love proof. Given that you have an isosceles trapezoid, we want to prove that AC and BD, we want to prove the diagonals are congruent. So we're given that ABCD is an isosceles trapezoid. So therefore we know what? By the definition of isosceles trapezoid. Dylan B, if this is an isosceles trapezoid, by definition, what two things are congruent? What makes it isosceles? No, by definition of the trapezoid. Why is this isosceles? Now, that's what we're trying to prove, that AC and BD are congruent. What makes a trapezoid an isosceles? What makes a triangle an isosceles triangle? Help them out, Riley. Since this is an isosceles trapezoid, what two things, by definition, do we know are congruent? Think of it like this, guys. If this is an isosceles triangle, what two sides are congruent? That's what makes it isosceles. Since this is an isosceles trapezoid, what two sides are congruent? Thank you. That's what we're going for there. And that is, by definition, of isosceles trapezoid. We also know that angle ADC, you'll find that, angle ADC is congruent to BCD. How do we know that? It's a base angle. If you have an isosceles trapezoid, base angles, base angles of a trapezoid are congruent, since it's isosceles. How do we know DC and CD are equal to itself? DC is equal to CD. How do y'all know that? It's the same thing. What says that? Reflexive property. So now look what we've got. I don't know if you can picture this. Let me do it in two separate colors. Different. There we go. Look at this triangle. In that triangle, do y'all see that you have a side, two sides, and an angle that are marked to be congruent to two sides and an angle of this triangle? You'll see that? Two sides and an angle of BCD is congruent to two sides and an angle of ADC. So by side, angle, side, aren't those two triangles congruent? You'll see that red and blue therefore would be congruent. So how do you know that AC and BD are congruent? The red and the blue triangles are the same in every way. What tells you, now that you know that red and blue are congruent, what theorem tells you that everything about them is going to be congruent? Starts with a C. C, P, C, T, C. Says that now that they're congruent, everything about them is congruent. So that's how you would prove that the diagonals are congruent. Okay. Here we go. Nearly done. The speaker shown is an isosceles trapezoid. So you have a speaker that's in the shape of an isosceles trapezoid. If the measure of JGH, which would be this one, measure of JGH is 85 degrees. FK is 8. FK, that's the distance from here to here. There's K. That's 8. JG is 19. The whole thing is 19. It says find the measure of angle FGH. Let's find the measure of everything. Since it's an isosceles trapezoid, the diagonals are congruent. So therefore, if this whole thing is 19, then this whole thing is 19. So what is this? That's 11. Okay. That hurt us a little bit. This is not FJH. Let's try that again. FJH, this whole bottom. There we go. That makes more sense. Whole bottom is 85 degrees. So what's the measure of FGH? Well, what's this angle going to be? Right here. 85 degrees. There you go. Since you have parallel lines cut by a transversal, if this is 85 degrees, then this would be 95 degrees. And if that's 95 degrees, since it's isosceles, then this would also be 95 degrees. And you've got, I don't know that we've got theorems that state it. You can look, there's a lot of symmetry here. If this is 11, this is going to be 11. If this is 8, this is going to be 8. Do you see that? So do you see that you've actually got some isosceles triangles? When you have these diagonals, you've got two isosceles triangles formed. So there's you some more things that you can use. We found all that. Let's try this one. You have a cafeteria tray that is an isosceles trapezoid. It says to save space at a square table, cafeteria trays often incorporate trapezoids into their design. Didn't know that. In WXYZ, if it's an isosceles trapezoid, the measure of YZW, which would be this whole corner right here, right? YZW is 45 degrees. Okay, stop there for a second. If that's 45 degrees, Carly, what else do you know? What else is going to be 45 degrees? The other, yeah, that one right there, right? XWZ is also going to be 45 degrees. And without even reading anything else, can anybody tell me what this angle is going to equal? That's 135 as well as this angle, 135. Good. Again, because you have an isosceles trapezoid. Anytime you have an isosceles trapezoid, the base angles are all congruent, and consecutive base angles will also always be supplementary just because they're same side interior angles. We're given that WV is 15. Let's do it in a different color here. WV, which is the distance from here up to here, is 15. You're given that VY is 10. From V to Y, that's from here up to here is 10. What would the distance from X to V be? 10 as well, right? The diagonals are going to be congruent. The diagonals are going to be proportional here, so that's also going to be 15. So the measure of what we were asked to find here, the measure of XWZ, yeah, that was pretty easy. It's 45. But I wanted to find it all because the next problem is going to ask you for other stuff. WXY. See, it's going to ask you for everything else as well. Okay, nearly done, guys. You have a quadrilateral with these vertices. I've already got it graphed here. Show that it is a trapezoid and determine whether it's isosceles or not. How do we determine Alex trapezoid? Remind me, what's true about a trapezoid? Two sides are parallel. Can you tell which sides it's going to be, guys? Is it going to be these sides? No, those are not parallel. Does everybody understand that? So let's test our red sides. Let me do a different color here. Let's test our red sides. Dylan C, what formula am I going to use to test for parallel? Distance, slope, or midpoint? In order to be parallel, two lines have to have the same width. Slope, yeah. So we're going to check our rise over run. You can go, well, this would be the easiest way. Down 2 over 1, that's -2. Down 2 over 1, that's -2. Does everybody understand that's a trapezoid? Okay. Show that it's a trapezoid and then determine if it's isosceles. Now, what are some methods we can use for is it isosceles? What's got to be true about diagonals? They got to equal. You know the easiest way to determine if it's isosceles or not? Yeah, 2 green sides. Just see if they're equal. So if I were you, I would learn how to use Pythagorean theorem. We've done that a million times this chapter. This has a side length of 1. This is 1, 2, 3, 4, 5. This has a side length of 1, 2, 3, 4, and 1, 2, 3. Hey, we know this one. 3, 4, 5. That length is 5. And this one is 1, 5. A squared plus B squared is root 26. They are extremely close. Is that, now if you were just looking at that, would you say, yeah, those are probably isosceles, right? They're not. Root 26 is going to be like 5.1. So you've got like lengths of 5 and lengths of 5.1. So are these angles going to be the same? No. Last one, then we'll pick up tomorrow with the rest of it. Is this, determine if it's a trapezoid and then determine if it's isosceles. I believe, let me get my shapes out here so it's easier to draw. I believe this side and this side, if it is a trapezoid, those would be the ones that are parallel. What do y'all think? Do those look parallel? And do you see how much counting you're going to have to do here? Here's my advice, folks. Why not label these? I should have to begin with. This is 0, 8. This is 6, 8. This is -6, -10. and this is -8, -4. And to save you from having to count, since there's such a big range in between them, use your formula. y2 minus y1 over x2 minus x1. Use your slope formula. Help me do that, Briley. Let's find the slope of this line first. Y2 minus y1, what do you get, Briley?
12.
Good. Over x2 minus x1.
8.
So 12 over 8. Wasn't that a whole lot faster than counting? And help me with my other line, Hunter. Y2 minus y1. 8 minus -10.
8.
Good. Over x2 minus x1.
12.
What do y'all think? We're going to have to reduce them, aren't we?
Yeah.
Divide by 4, you get 3 halves. Divide by 6, you get 3 halves. It's a parallel, excuse me, it's a trapezoid for sure. But now let's determine, is it isosceles? I like this one. Let's draw our sides here. Because watch. From 0,8 over to 6,8. Can anybody tell me how far that is? 0,8, 6,8. You went over 6. So we've got, in order for this to be isosceles, the distance from here to here would have to be 6. Let me draw a straight line if I can find it. There we go. The distance from here to here must be 6. Now, I don't want to, let's say that, let's just get some extra practice with our distance formula. We never use it. Distance formula is the square root of x2 minus x1, which is -6 minus -8, which is 2, plus y2 minus y1, which is 6. So that's the square root of 4 plus 36. That's the square root of 40. Pretty close to 6, though, isn't it? But not exactly 6. So it's going to be like 6.1, 6.2, somewhere around in there. Not an isosceles. In your other method, if you wanted to, you could have found the distance. To see if it's isosceles, find the distance of the 2 diagonals. If the two diagonals are equal in length, then yes, it would be isosceles.